Hello everybody, I'm Mark Tewksbury, your host for this program. Our goal is to reveal the methods and materials that go into the everyday products that you see around you, from toothpicks to computers to airplanes. If you thought you knew something about these items, you might be in for a surprise. There's a whole world of things waiting for us to discover on how it's made. It all starts with a cocoon. Making one with worm silk is the work of a butterfly caterpillar, and it matures within it. It weaves its cocoon in 3 or 4 days using 2 saliva threads from its lower lip. Remarkably, a single cocoon yields up to 1.5 kilometers of silk thread. In this program, aluminum foils, snowboards, contact lenses, and bread. Oh, the magic of aluminum foil. You can use it to heat something up in the oven or keep something cold in the fridge. But how do they transform that big piece of aluminum into this thin little foil? The manufacture of aluminum foil requires the repeated thinning out of a large block of aluminum. We begin by melting ingots of 100% pure aluminum in a natural gas furnace. These ingots, called pigs, are essential in alloys with zinc, titanium, and silica. It takes 3 to 8 hours to melt 27,000 kilos of aluminum in this remelting furnace, which operates at 750 degrees centigrade. The fusion temperature of aluminum is 660 degrees centigrade. A portion of aluminum is poured into this small mold to make a sample. Solidifying in just seconds, the sample allows for testing to verify the contents of the prepared alloy. This trough is used to transfer the aluminum from the remelting furnace to the tapping well. Molten aluminum runs in a movable trough located above the tapping well. At this stage, impurities are filtered out in special receptacles. The molds are cooled with water to accelerate the solidification of the molten aluminum. Ingots are unmolded and are ready for milling. Each ingot is massive, measuring 4.4 meters in length, 1.4 meters in width, and is 45 centimeters thick. It weighs a whopping 7,500 kilos, so it has to be handled by overhead cranes and placed on special plates. This crust-removing machine removes 3 millimeters of the ingot's thickness. Impurities are eliminated to achieve a perfectly smooth finish. All traces of the liquid used to cool the decrusting knives have to be eliminated. The many steps in the thinning of the ingot begins. The aluminum block is crushed by the hot mill rollers. Temperatures in the rollers are between 455 and 540 degrees centigrade. Pressure on the ingot is continually verified by a technician. If too great, it's lowered and the technician then adjusts the pressure. The heat is so high that the ingot risks sticking to the mill's roller. To prevent this, everything is cooled with a liquid that's 95% water and 5% oil. Starting from a thickness of 45 centimeters, the ingot becomes increasingly thinner with each pass-through. Depending on requirements, the ingot will go through the machine between 12 and 16 times. The ingot now measures 7 centimeters in thickness. It has to get down to just half a centimeter. At this stage, the ingot is 5 centimeters thick and measures a little over 9 meters in length. This conveyor transports the plate during its milling stages. The ingot has now become a 5 millimeter thick sheet. It is sufficiently thin to proceed to spooling, where it spools onto itself before being sent to the cold rolling mill, where its thickness will be reduced still further. The aluminum sheet has become very thin now and risks being broken by the tension needed for cold rolling, so the sheet is doubled to avoid this breakage. One final reduction in the mill, and the sheet will have the thickness required by the customer. A liquid coolant is used to prevent the foil from sticking to the rollers. Since the edges of the foil sheet are lightly damaged and crinkled, a knife removes a 1 centimeter thin strip. Finally, the roll is cut to the desired width, and one huge ingot has produced foil measuring 12.7 kilometers in length. If you've ever tried to ride on a snowboard, you know it's not as easy as it looks. Well, the making of a snowboard is much the same. There's more to it than meets the eye. The snowboard is the delight of winter sport enthusiasts. Its core is made of a thin sheet of wood. Various kinds of woods are used depending on the type of board being made. Bindings have to be firmly attached to the board. Holes are drilled for inserts to which bindings will be secured. A template allows the holes to be precisely drilled. Planing reduces the board to the required thickness. A thick board is obviously more rigid than a thin one. A shaping procedure refines the board's contours. At this point, the board is still perfectly flat with no curvature as yet. The boards are then stored upright to await the next step. Now they must secure the aluminum inserts which will be embedded in the wood. This thin sheet of fiberglass will afford better support for the inserts. They will thus be more solid. To make working on it easier, the board is securely held in place by clamps. Epoxy, an extremely strong adhesive often used with composite materials, is applied to the fiberglass at room temperature. It is then essential to remove any excess epoxy as well as to eliminate all air bubbles so that there will be a good adherence. As for the top part of the board, it's made of a resistant plastic applied by silk screening. In silk screening, ink is spread by this little squeegee. This application is called a pass. Colors have to be applied one at a time. Inks must be allowed to dry for several hours between each coat. Now the board must be curved. A cover is placed on the mold. When the mold is closed, the board is given the desired curve. Heat trapped in the mold makes the epoxy set and harden. The board comes out of the mold and any excess epoxy and wood are removed by a bandsaw. To achieve a perfect cut, the saw blade is changed every 50 boards. It's highly precise work and totally manual. They apply, again by silk screening, another coat, then another color. This time, the red. The snowboard must now be protected. A protecting varnish flows as a thin curtain. The board passes beneath this curtain and then moves into a dryer for a 6-hour stay. Sanding removes surplus varnish from the edges of the board. New holes are pierced into the board to locate the inserts installed at the beginning of production. This sander removes imperfections in the hardened varnish and prepares the board for its second varnish coating. Then the plastic base is sanded to obtain the desired finish. The board is checked to see that it's perfectly flat. A razor blade verifies that the different coats are well adhered to one another. Certain boards get an engraved aluminum insert, a luxury touch. The board is finally now ready for action. This facility turns out over 500 snowboards per day in a range of some 30 different models. When most people take off their glasses, everything becomes fuzzy, except when they're wearing these contact lenses, which help you see without anybody being aware that you've even got them on. Contact lenses have been in existence for over a century. At first completely rigid, they have now become gas permeable and as flexible as gelatin. These small polyhema discs are used to make soft polymer contact lenses in a variety of colors. We see here a patient's prescription, essential to the fabrication of lenses. The process begins with data processing control of the shaping. Data is supplied by computer, which controls a digital lathe. They begin by shaping the inner curvature of the lens. This digital lathe, rotating at 6,000 revolutions per minute, is equipped with an industrial diamond. It shapes the inner surface, the part that touches the cornea. It must be free from any abrasion and imperfection, and is polished with a superfine abrasive paste. Polishing is a crucial step because it assures excellent comfort and perfect vision. A technician measures lens thickness with an extremely precise gauge. They now shape the outer surface, the part which touches the eyelid. The lens is glued with a special warm wax, and when the lens is completed, the wax will be removed by an ultrasound device. The wax takes on the desired shape in just seconds. The comfort of a lens is also determined by its thickness. It must be as thin as possible while retaining sufficient solidity. They begin by shaping the outer diameter of the lens, which takes only a few seconds. They now polish the outer surface of the lens. This polishing, done at high speed, calls for an abrasive paste, some oil, and a small polyester cotton ball. This apparatus polishes several lenses at the same time, a step that takes only 60 seconds. With everything computerized, quality is incomparable. A technician then polishes the rims of the lens. The polymer is then hydrated to make it flexible. Lenses remain immersed in a balanced pH saline solution for 24 hours. The lens becomes engorged with liquid and expands, reaching the desired proportions. This optical topographer is used to verify, through color distribution, whether the spread of optical power in the lens is precise enough to assure perfect vision. And now we proceed with another important testing procedure. The soft, fragile lenses are always handled with the greatest of care. This unit, called a frontofocometer, is a metering device which verifies the optical precision of the lens. Lenses are now completed and are cleaned, and they're stored in containers filled with a salt solution. This little vial that we find at optometrists is perfectly sealed with a silicone cap and another of aluminum. These vials are placed in a sterilizer at a temperature of 121 degrees centigrade for an hour and a half. The contents will remain sterile for a period of up to 7 years if not opened. The production of a lens involves 14 steps. If we exclude the rather lengthy hydration process, actual lens production requires only 15 minutes. They can produce almost 1,000 contact lenses per day, all made from these tiny colored discs. Bread, so delicious, smothered in butter and jam, dipped in gravy, or used to make big, yummy sandwiches. Who can resist it? I can't. Some 1,300 years ago, in the time of King Tut, Egyptians were already baking 40 varieties of leavened bread. The Greeks' contribution to this history was the oven, and 70 varieties of flavored breads. Breads so good that the Romans took the Greek bakers to Rome and their ovens to Gaul. This is how, by the Middle Ages, bread had become the primary food of Western Europe. Multigrain bread is made from several ingredients, such as flaxseed, buckwheat, soya, and millet. This protective grill prevents foreign matter from accidentally falling into the recipe mix, a recipe calling for some 600 kilos of flour. The ingredients, ground in a mill, are kept in these 36 enormous containers. We begin by mixing the ingredients together. These kneading troughs are used to ferment the yeast, a step which takes 3 hours. The fermenting yeast makes the dough rise considerably. This huge mixer kneads the dough for about 8 minutes. When thoroughly homogeneous, the content is emptied into a large tub. The dough weighs 1,000 kilos. That's almost a ton. The dough is loaded onto a slide situated above the dough divider. At the bottom of the machine, a small hole allows the dough to escape. 2 mechanically operated arms cut the dough pieces into equal lengths. It forms 192 of these a minute. The dough then falls onto a conveyor. Here, dough pieces are rolled into balls, which can be more easily worked. The dough balls are floured to prevent them from sticking during their transport and when they're molded. Here the balls of dough leave the divider and go to the molder. During transport, the dough can rest, allowing the yeast to act. The dough is then folded and rolled. The machine can handle 3 per second for a total of 11,500 an hour. The dough is rolled out to the exact size and falls into baking molds. Here we see the making of hot dog rolls. These little dough balls have to be shaped lengthwise and fermented before molding. Here the hot dog rolls are being machine molded. Dough pieces must not touch one another, so they're spaced apart by a small mechanical arm. Now we go back to multi-grain bread production. Squatted down at the bottom of the molds, the dough pieces go into the prover, where they rise for an hour at 42 degrees centigrade and at 70% humidity. Then they bake for 20 minutes at 255 degrees. When finally baked, the loaves end up with a nice golden color. A vacuum system draws the loaves from their molds. They're then placed on a conveyor to cool. A guidance system takes care of carrying the breads to various sections of the bakery. When well cooled, breads go to the slicer, which cuts 65 loaves a minute. They are sliced by 2-meter wide and 40-centimeter long steel saw blades. These blades are changed every 2 weeks. Sliced loaves are automatically packed at 65 per minute. They're now ready for shipping. Some 5.5 hours have passed between preparation of the dry flour and packaging of the baked bread. They say a picture's worth 1,000 words. I hope what we've shown you today speaks for itself. Our goal was to give you a view of the many manufacturing methods that produce the items we see in our everyday lives. I'm Mark Tewksbury. See you next time on How It's Made.